Hey everybody, this is Dr. Retzik with you again. This is our third video in Math 406, and it's a continuation of our discussion in section 6a. So this is 6a continued. And it's all about seeing what kind of structure inner products give us inside a vector space. So the setting at the moment is we have a vector space V. It's just a big box of stuff. There's something in there playing the role of the additive identity. And then there's other objects in there, say U and V, and you can add them together if you like. It's just a big box full of stuff. And this box is what's called an inner product space. So all that means, again, is it's a vector space equipped with an inner product. And that's where, really, the entirety of our Math 406 is going to take place. Now, when the vector space is something familiar, like say R2, then we think of the objects inside that vector space as like actual arrows, vectors, and we think of them as having length and direction, and we can start talking about the magnitude of a vector. The beauty of having an inner product on an abstract vector space is that it still allows us to talk about magnitude. And that leads to our first definition today. Definition: the norm. So that's the word we're defining, the norm of little v belonging to big V is the symbol for it. It looks like the symbol for magnitude for a vector, like from calc class. So you put little v inside these double absolute value bars. The definition, so this equal sign is a definition. We're declaring this to be what we mean by the norm of a vector. It's none other than the square root of the inner product of v with itself. And this is meant to mimic what's happening in R2. You remember back in R2, the magnitude of a vector is simply the dot product of that vector with itself, all square rooted. So it's still true here, only now we've lost all sense of these objects as being sort of actual arrows with actual lengths. And all we really have is this notion of norm given by our inner product. Now, a couple of things follow easily right off the bat. So here's some easy properties. Easy props of the norm. So for example, here's one. Easy property of the norm. The only way a vector has norm 0 is if that vector is the 0 vector. So the only way the norm of v comes out to 0 is if v is 0. And this gives us another opportunity to do that thing where we kind of make sure we know what we're talking about on both sides of the equal sign, and on both sides of the if and only if, for that matter. So the first statement, magnitude v equals 0. The 0 in that statement, this 0 right here, that's 0 the number, just the number 0. On the other hand, the 0 on the other side, that's 0 the vector. That's the vector back in our vector space right here, serving as the additive identity. And so what that first easy property says is the magnitude of a vector is 0 if and only if that vector is the 0 vector. And that actually follows immediately from the definition of inner product. Remember the 5 things that go into the definition of inner product? The second thing was definiteness, and the only way the inner product of a vector with itself comes out 0 is if that vector is 0. So that follows immediately just from the definition. Here's another easy property. If you have a scalar times the vector v, and you wonder what its norm is, well, it's easy. The scalar just pops out. And this makes sense too, because back in R2, if you double some vector, then it's twice as long. And so that happens here too. That scalar simply pops out as absolute value lambda, and then times the norm of v. So you're allowed to pull scalars out of norms, but just remember, you're pulling the absolute value out. The norm is always bigger than or equal to 0. All right, so norms have these nice properties, but the main thing that the norm is going to purchase for us is a way to start talking about perpendicularity inside our vector space. And this is a huge breakthrough for us. Look back at our drawing. This is just a box of stuff. Yet now, we're going to be able to start talking about whether certain things in there are perpendicular to other things in there. And it's going to model our sense of perpendicularity from R2, but it's in this much more abstract setting. Only we don't use the word perpendicular. We use the word orthogonal. So here's the definition. U and V belonging to big V are orthogonal. So that's the term we're defining. Orthogonal. Simply if their inner product comes out to 0. Now that's 0 the number. Remember, inner products produce scalar values. Yeah, so 2 vectors are orthogonal precisely if their inner product is 0. All right, now, as soon as you're willing to talk about vectors being orthogonal, then all this geometry, stuff that is sort of visually clear from R2, remains true in these much more abstract settings. And the first theorem is kind of a big one. It's on everyone's top 10 all-time theorems. We have something in an inner product space called the Pythagorean Theorem. This is the Pythagorean Theorem. All right, so back in the old days, Pythagorean theorem was something about triangles. This one is telling us the relationship between the norm of u plus v and the individual norms of u and v. In particular, if u and v in big V are orthogonal, meaning their inner product is 0, then the square of the norm of their sum is the sum of the squares of their norms. So there's a connection between the norm of u plus v and the individual norms of u and v. Now, there's a strong visual here before we get to the proof. Here's the visual. The visual for the Pythagorean theorem comes from thinking about it in an R2 sense. Okay, so say you had this as your vector u, and say you had this as your vector v. And all of this was happening literally in R2, two-dimensional space, the xy plane if you want. Then that's your vector u plus v, what, by like tail to tip method or whatever they used to call that back in the day. And since u and v are orthogonal by hypothesis, that means this is a right angle. That's what orthogonal means. It means perpendicularity when it's genuinely R2. Then you can see Pythagorean theorem is simply c squared equals a squared plus b squared. The old-fashioned Pythagorean theorem. The one from thousands of years ago. So that's the visual. Maybe we can box that up. Let's box that visual. This is our motivation for the abstract theorem that we're choosing to call the Pythagorean theorem. Okay, now, the proof itself is actually super straightforward. It's the cleanest thing. Here's the proof. Well, the theorem's an if-then, so let's suppose u and v in big V are orthogonal. Under that supposition, we have to argue now that the square of the norm of the sum is the sum of the squares of the norms. Okay, well, let's just start with the left-hand side of the thing we're trying to show. We know that if you're interested in the square of the norm of a vector, that is by definition the inner product of that vector with itself. That's the very definition of the word norm. Look, let's scroll back. Here it is, right here. The definition of norm is square root of inner product. So if you're interested in the norm squared, it's simply the inner product of that vector with itself. Now, inner products, you guys know, have lots of nice properties. Some directly from the definition, others that follow from the definition. But you got additivity in the first slot, say, and additivity in the second slot. And so if you take this inner product and kind of foil that inner product out, I think you get this. You get inner product of u with u plus inner product of u with v plus inner product of v with u plus inner product of v with v. Now, this first term is nothing other than the norm of u squared. The two middle terms, this one and this one, are both 0 by supposition because the vectors u and v are orthogonal. So when you take their inner product, you get 0. Thus, those are both 0. That leaves you with this last one, which is nothing other than the norm of v squared. And that's it. The proof is over. So this is a geometric statement, but it's happening in a very abstract place. And it follows simply from the properties of the inner product and the definition of norm in terms of the inner product. So that's nice. We have a Pythagorean theorem. Now, one last geometrical idea that also presents itself in this new abstract setting also comes from Calc 3. So I want you guys to think about this picture back in Calc 3. Old Calc 3 picture. Back in Calc 3, you sometimes drew stuff like this. You would have an arrow, like let's say that's the vector v. And then you'd have some other arrow, and that's the vector u. In Calc 3, we were sometimes interested in the amount of the vector u that was in the direction of the vector v. So if you drop straight down, whatever that means, perpendicularly, I suppose, and you try to think about the part of the vector u, the component of the vector u that points the same direction as the vector v, maybe you think of it as that green arrow. And then the component of the vector u that's perpendicular to v, maybe you think of as that red arrow. Well, in Calc 3, we actually identified the green and the red arrow. In fact, the green arrow had a name, I think. This green arrow, I think in Calc 3, we call it the projection. So that's proj of the vector u onto the vector v. It's got that really kind of clunky notation, but that's what that green arrow was called back in the day. And whether or not you remember why it was what it is back in the day, this is what it turned out to be. So you got the projection of u onto v. Now look at it for a second. That green arrow, that points in the same direction as v. It's not nearly as long as v in our picture, but it points in the same direction, so it must be a multiple of v. So the only question is, what multiple? And when the dust settles and you do a bunch of dot product stuff, law of cosines, etc., back in Calc 3, when the dust settled, this is what it turned out to be. It turned out to be u dot v over magnitude v squared. So in the parentheses there, that's just a number. That's a scalar. All times vector v. That was the old picture back in Calc 3. The claim is we have a similar notion here in linear algebra in this much more abstract setting of an inner product space that models that old drawing from Calc 3. So the last thing we want to do is think about orthogonal decompositions. And that's just fancy language for the picture we just drew. So let's write that down, and that'll be it for today's intro. So here, in our abstract, inner product space, V, still, we can write an arbitrary vector u as some multiple of another vector v plus a vector perpendicular to v. And the way we do it is to just steal the multiple from the old Calc 3 setting, only we're going to write it not with dot product, but with inner product. So here's how you break u up into something parallel to v plus something perpendicular to v. Okay, here we go. Here's the parallel piece. This is the green piece in the drawing we were just looking at. Okay, here we go. You do the inner product of u with v. You divide by the square of the magnitude of v. All of that in the parentheses is just some number. You multiply all that times v. So that is pointing in the same direction as v. It's a scalar multiple of v. It's in the one-dimensional subspace spanned by v. Say it however you want. That's a multiple of v. Now, if you're going to balance the books algebraically, the thing you add to that multiple of v must be u take away that multiple of v. So the second piece, the red piece in the drawing that we were just looking at, is the second large parenthetical term. Now, you can't argue algebraically with the equal sign, because basically that equation says u equals something plus u take away that same thing. So for sure this is true. The equal sign is not in dispute. The beauty of this decomposition is that not only is it algebraically true, but it really did break u into two pieces. There's this piece, which is a multiple of v, and there's this piece, which is orthogonal to v, where orthogonal means what we said it means. If you take the inner product of that red piece with v itself, you will get 0, and I invite you to do it. It's fun to check and see all the algebra settle and have that inner product come out to 0 before your eyes. So this is an orthogonal decomposition of u into two pieces, one parallel to v and one perpendicular to v. And it goes with the old Calc 3 picture that we were looking at right here. And that's it for now. We're going to talk more about norms on Monday, and we're going to see some even more striking and more useful geometric structure start to emerge from inner products and their connection to norms in an inner product space. All right, you got enough to read, and be ready for class on Friday so that you can ask questions and we can keep getting these new ideas and this emerging geometry dialed in. All right, I'll see you next time. Bye.